Hi guys, so welcome to another video. So today we're going to be looking at series, which is chapter 3 on the Excel Core PO1 textbook. So as before, there's a prior knowledge checklist. You can pause the video and have a go at this. So here the answer for question 1, A, B and C, and for question 2, A, for B and for C. Okay, so we'll move on. So sigma notation is used for sum of series, and you would have seen something similar to this when you done a geometric and arithmetic sequence in the A-level maths. So when we have a sigma notation like this, the sequence of numbers are defined. The sequence of numbers we are finding the sum of. So that's what this bit is telling us. The first value we start off in the sequence, that's the number goes at the bottom here, and at the top the last value we put into the sequence formula, but in every integer in between as well. So this is the starting point and the top is the end point, and the bit in the middle is where it's defining the sequence. So in this case, if we plug in r equal to 1, we get 9, r equal to 2, we get 19, r equal to 3, we get 29. And the sigma is just saying sum, so we just add them up, gives us 57. So here's another one. The sequence of numbers we're finding the sum of, we're starting from r equal to 2, and we're going all the way up to r equal to 5. So you guys pause the video and have a go at this. Okay, so that gives us an answer of 54. So to find the sum of a series of constant terms, we can use the formula. So if we're adding up 1 plus 2 plus 3 plus 4 all the way up to n amount, we just put sigma 1 equals to n. And this is essentially saying the sum of n ones is equal to n. So for example, the sum of 1 plus 1 plus 1 is equal to 3. So the sum of 1 plus 1 plus 1 plus 1 plus 1 equal to 7. So to find the sum of the first n natural numbers, so 1, 2, 3, 4, 5, all the way up to n, you can use this formula. So sigma r is equal to half n, n plus 1. Now this should look quite familiar from arithmetic sequence from the A-level maths. So this is essentially saying the sum of n natural numbers is equal to half n bracket n plus 1. So for example, the sum of 1 plus 2 plus 3 plus 4 plus 5 equal to 15. So we could just simply do half times 5 bracket 5 plus 1 equal to 15. Okay, and we'll see how to prove this later on in the chapter. So now, what I need to do is calculate the sum of the series for this one. So you guys pause the video and have a go at this. So we want the sum of the first 50 numbers. So starting at 1 all the way up to 50. So we plug into the formula. So half bracket 50, another bracket 51. So if we calculate this, we get 1,275. And obviously, you could also write it in that form if you prefer. So have a go at this one, pause the video and work through this. So this time we are starting from 21 and we're going all the way up to 60. So the sum of the numbers from 21 to 60. So click on number line. Okay, will be equal to the sum of numbers from 1 to 60. Subtract the numbers from 1 to 20. Okay, so if we go from 0 to 60 and then minus 1 to 20, that would be another way of working that out. So we could write this as sigma r equal to 1 to all the way up to 60, and then minus r is equal to 1 up to 20. And this is another quick way of dealing with this. And be careful, this number here has to be one less than where we're starting from, because where we're starting from is inclusive. So now if we work out each one of these, so we've got 60 times 61 over 2 minus 20 times 21 over 2, and now if we calculate this, we get the following. So the sum of numbers from 21 to 60 is 1620. So you can split up series sums of the form. So if you have something like this, sigma AR plus B, you can split up into two separate series sums as follows. So you could put A outside, because A is just a constant value, right? So we could put the A outside plus B lots of sigma 1. Again, B times by whatever you have here. So that's going to be important for us to remember. You could separate these two together. So this allows you to then use the sum formula for the. So if we take an example, let's say show that sum of 3r plus 2. So we could write it in this form. So if we start by writing the first few terms of the sequence, so this is equal to the sum of the multiplied terms added to the sum of the twos. And we can factorize 3 out of the multiplied terms and factorize a 2 from the added terms. So this is multiplied by the sum of the first n numbers, represented by the formula r. So in this case it would be the 3 outside. This is 2 multiplied by n ones outside. So we could leave the 2 outside like this. Okay, so you guys pause the video and have a go at this one. Okay. So again, we're going to split these up. So if we take the 3 outside, and so for the first one, 3n, n plus 1 all over 2, and then we've got n lots of the 1. So in this case, our n is 25. So 3 lots of 25 times 26 all over 2 plus 25 times 1. So that gives us 1000. So for the first 25 terms of the sequence of formula, 3r plus 1 will add up to 1. So we've got to show that question. 7r, sum of 7r minus 4 equal to n over 2, 7n minus 1. So the sum of the first n terms of the sequence is given by this formula, where n is the number of terms. So in this case, we start as normal, but use n instead. So we split up the two separate sums. We remember the 7 on the first expression. And also minus 4 lots of n. So we're at 4n as a fraction over 2. So we have a common denominator. And if you group the terms together, expand the bracket. If you group the terms, so if we finally factorize this, we could see 7r minus 4 is indeed equal to n bracket 7 minus 1 all over 2. The second part of the question, the word hence is used, so we need to use what we got from earlier. Calculate the value of the following. So you guys pause the video and have a go at this. So again, remember we're not starting from r equal to 1, we start from r equal to 20, so you just need to be slightly careful here. So we could rewrite this in this form, just like what we did on the previous slide. So for the first one, n 7n minus 1 over 2, because that's what it can be written as. And for the second one. So now, n on this one, we're going all the way up to 50. So you're replacing n with 50. And for the second one, we're going all the way up to 19. Remember, 19, it has to be 1 less than the r equal to 20. So n would be 19 in this case. So if you calculate each one and subtract, we get 7,471. Alright guys, so test your understanding by having a go at this sort of questions here. So pause the video and have a go at this. Okay, so for the first one, if we set it up like this, because it's saying sigma AI plus BI, so what it actually means is A1 plus B1 plus A2 plus B2 all the way up to AN plus BN. So if we just group them together, pull the A's together plus the B's together, so you can see it can be written in this form. So for the second part of that question, again, we're just working out from r equal to 1 to 25, and it's 3r plus 1. So if we split these up, we get the following. So that gives us 1,000. For the next question, again, it's one of those show that question. So the trick here is, same as before, you could just always take the factor of the 3 out, and then 2 out, and then write in that form. And where it says hence calculate, where you just plug in the numbers, and we should get 3,317. So the sum of the sequence of squared numbers is given as, so if we have r squared, sigma r squared, it can be written in this form. n plus 1, 2n plus 1 all over 6. Or simply you could just put as n over 6, n plus 1, 2n plus 1. And this is how it's usually written in the formula sheet. And the formula for the sum of the sequence of cube is sigma r cubed n squared bracket n plus 1 all squared all over 4. Or on the formula book, you'll find it written as n squared over 4 bracket n plus 1 squared. Again, we will see proofs for this in chapter 8. So we want to evaluate this here. Start from r equal to 1 to 30 r squared. So we write down the formula. We substitute n equal to 30, as we want to go from 1 to 30. And once you simplify and then calculate, get 9,455. Okay, so you guys pause the video and have a go at this. Working out from r equal to 20, remember, from 20 to 40, and it's a cube, r cubed. Okay, so if we write this from r equal to 1 to 40 minus r equal to 1 to 19. So now if you work out from 40 and then to 19 using the formula, if you plug in your n values and you calculate, and then minus the 36,100, so the final sum should be the following. So 636,300. Okay, so let's have a look at this one. This one we're starting from r equal to n plus 1 and finishing at 2n, and it's r squared. So this one is more algebraic. We still can approach it in the same way. The first value we put in the sequence will be n plus 1, and the final value will be 2n. So we want the sum of the first 2n terms, subtract the first of n terms, same as we were using the numbers. So we could write this like this. So we're going from r equal to 1 to 2n minus r is equal to 1 to n. So we write out the formula twice and then substitute 2n in the first and the n on the second. Okay, so we could write this as one fraction, this all over 6. And this is the key step. You can factorize n, 2n plus 1 is a common to both terms. So if we take this out here, and then we'll introduce a square bracket so we don't get confused with all these so many other brackets. So we'll have 4n plus 1, and for the next one we'll have minus n plus 1. So expand the terms in the square bracket, and then if we tidy that up, we see we get n, 2n plus 1, 7n plus 1 all over 6. So the factorizing step here is crucial, otherwise you end up trying to factorize a cubic, which can take a long time. So now it says find, and you're given this, verify the result is correct for n is equal to 1, 2, and 3. So as we've got the formula now, if we replace n equal to 1, on the left hand side, the first number we put in is 2, which is also the last number we put in. So we should get just 4. So the number in the sequence just add up to 4. So let's check with the formula. So putting n equal to 1. So if you substitute that in, you get 4, as we expected. And now if we try with n equal to 2, okay, so the first number we put into is 3. So we have 9 and 16. So the numbers add up to 25. So now if we check with the formula, substitute into the formula, we get 25. And same with n equals to 3. We substitute that in. So the first number we put in is 4, and the last number put in is 6. So again, 16, 25, and 36. So the numbers add up to 77. Now if we substitute into the formula, we also get 77. So indeed we have verified the result, and the result is correct. So the formula seems to be working fine. Okay, so welcome back to another video. This is part 2 on series. So we have a question here where we're told to work out the sum of r squared plus r minus 2. We have to show that is equal to n over 3, n plus 4, n minus 1 in bracket. So we're going to write this as before in separate sum. So we could write this as sigma r squared plus sigma r minus 2 lots of sigma 1. And if we write the formula for each one, and we've seen in the last video the r squared, the sum of r squared can be written as n plus 1, 2n plus 1 all over 6. And sum of r is just n plus 1 all over 2 minus 2 lots of n. We write down the common denominator. So it will be 6. So we can write all over 6. And now we could simply group them together. And if you recall from previous presentation on series, you have to be a bit more clever on how you factorize this. So one way to do it is look at what's common everywhere first, including the bracket. So first of all, we've got n, n, n. And in this case, there's no bracket that's common because we just have 12n at the end. So we just take n outside. So we're left over with n plus 1, 2n plus 1. And then here we go just 3n plus 1 and it's minus 12. So the next step what we want to do is expand the brackets and then simplify inside the bracket. So if we FOIL the first two sets of bracket and multiply this out, and we'll group the terms together. So we've got 2n squared plus 6n minus 8 all over 6. And we just need to make it look like what the question is said. So here they're all even, so we could take factor of 2 outside. And then simply the 2 and 6, we could just simplify that further down. And now we've got quadratic inside the bracket. So if we factorize the quadratic, it will give us the result. And this is what it's said to show. So you can see there's a huge amount of algebraic manipulation involved here. Okay, and usually this type of question would have a second part to it in the exam. So here we're told, hence calculate sum of the series 4 plus 10 plus 18 plus 28 plus 48 plus ... 418. So if we start off with r equal to 1, so we substitute it in 1 squared plus 1 minus 2, and that gives us 0. set r equal to 2, so 2 squared plus 2 minus 2 gives us 4. R equal to 3, 3 squared plus 3 minus 2 equals to 10, and so on. So you can see that this formula gives us a sequence we're trying to find the sum of. The 0 at the start will not affect the sum, so it can be ignored. And we go all the way up to r equal to r. Okay, and in this case, the last one is 418. So first we need to know how many terms there are. So we have to find the value of r, which gives us the term with the value of 418. So if we simply just equate r squared plus r minus 2 equal to 418 and simplify, now you see you got yourself a quadratic. So if we factorize the quadratic, we get two answers. Only one of them is possible. So we have r equal to 20 and r equal to minus 21. So we need r equal to 20. So we're finding sum of the first 20 terms of the sequence. We can use the formula we're given, because we're told all of this is equal to that. So we just substitute n equal to 20 and calculate, and it gives us 3040. Okay, find a formula for sum of the following series. So you guys pause the video and have a go at this. Okay, so the first thing obviously to do on this one is to expand the bracket. And after expanding the bracket, we could write these as three separate sums. And the coefficient of the 2, just simply take that outside. So we have 2 sigma r cubed plus 5 sigma r squared minus 3 sigma r. And then using the formula, so with the formula at the top here, substitute this in and simply multiply by 2 on the first one, 5 on the second one, and with 3 on the next one. And now we could give this all a common denominator. So common denominator, give it all in terms of 6. We combine, and then a little bit of clever factorization here. So you can see there's n plus 1, n plus 1, n plus 1, and also there's n, n, n. So that would be the smart thing to do here. Take n and n plus 1 outside, and then inside we'll have the remaining, so which is 3n, n plus 1, plus 5, 2n plus 1, and minus 9. So now we could just think about expanding the inside of the square bracket. Okay, so once you expand that, we can simplify, and we get the following. Okay, so you substitute in the values of r going 1 to 40 and r going from 1 to 10. You minus 1 from the other, and we'll do the calculation, and you get the following result. So 1445230, so 1.4 million-ish. Okay, so here's a past exam question. It's worth 10 marks, got part A and B to it. So you guys pause the video and have a go at this. So okay, so for part A, it's a show that question. And again, same as before, you expand the bracket, you write each one separately, separate them, and you should be able to show it. And for part B, as I said, there's always a part B follow, hence that or follow through question. So this is the solution. So here we're looking at A as 13, B as 36, and C as 26. Okay, so here's another exam question, a bit harder this time. Again, it's from class paper, A and B. This one's worth 7 marks in total. So pause the video and have a go at this. Okay, so here on part A, it's a show that question. Same as before, we could start separating them. And then once you show that, well, you know you got it right. And for part B, again, you have to be careful because it's starting from r equal to 20 to 50. So we do r from 1 to 50 minus 1 to 19. So in summary, these are the formula that will be given in the formula sheet. You just need to know how to apply it. And again, it's the algebraic work you have to be slightly careful of.